Hello, everybody. So what we're going to be looking at today is section 10.1 in the book. So this is section 10.1. So we're starting a new chapter. We're done with chapter 5. And yeah, this should be probably a topic that you guys enjoy more than all of those induction proofs that we had to do. So from here on out, from here till the end of the semester, the material is going to be a lot more kind of, here's some simple definitions, here's some new kinds of stuff that you've never seen before, but it's not going to have a lot of proofs. So we're in large part done with proofs. I won't say completely done because there's going to be times where you don't prove something, but you have to see a proof. I'll do the proof, you watch the proof, then we're done. So yeah, so that's how it is. Let's go ahead and get started. So 10.1 graphs. So let's just start with a precise mathematical definition here. Let me get a pointer. So a graph is defined by two sets, actually. So there's V and then there's E. It actually doesn't matter what you call them, I suppose, but two sets, V and E. V is going to be what we call vertices. So V for vertices, obviously. E is a set of edges. So every edge either has one or two vertices associated with it called endpoints, and an edge is said to connect its endpoints. So we will look at them momentarily, but I'll just draw one before we scroll down here. What we're talking about is this. So a dot is a vertex, like that. And an edge is just a line connecting a vertex. So like you can call that E1 if you want. And you can call that E2 if you want. And your vertices, call them whatever you want, maybe V1, V2, V3. And so that's all we're talking about when we're talking about a graph. And so in the graph that I just drew, right, the V would be, it's the set of vertices. So this is what I called them. And then E would be the set of edges, which, what did I call them? E1, E2. All right, and then altogether, that's the graph. If you know the vertices and you know the edges, you have the graph. So it's really pretty straightforward. It's just dots and then lines connecting the dots. And they say somewhere each edge has either one or two vertices associated with it. Well, you don't see that here, but you do when you look at the graph, right? Like V1 is here, V2 is over here, and obviously E1 is associated with these two vertices because it connects them. Now, why would a vertex be only associated with one edge? Or sorry, why would an edge be associated with only a single vertex? Well, you can have an edge go to itself, one vertex to itself. So that'd be like E3 now. So that vertex that I just added, E3, it connects vertex 3 to vertex 3. So there's only one vertex associated with it. And that's called a loop, and that definition will be, down below. So let's actually scroll down to where these things are all defined now and see how it looks. So yeah, I'll just comment on what I said here. There's not really a great convention for naming edges or vertices that your book will keep to. So, you're just going to get used to people naming edges different ways. That's all. Or just numbering them, right? If you're on a computer, then you don't really give them names. You just have like some list in the computer that's storing vertices, and they're just like 1, 2, 3, 4, 5, 6. 6 vertices, numbered 1 through 6. Anyway, let us keep going. So here's some examples. So V1, V2, V3, E1, E2 describes a graph with 3 vertices and 2 edges, but it doesn't tell us which vertices are connected by the edges. And that's what we just talked about, right? Like you see E1 and E2 and you say, okay, that's 2 edges, but where are they? It doesn't say. So that's why it's not a great way to name edges that way. But we can still draw it, right? Like, so V1, V2, V3, we can draw them however we want. So I'll draw them like this. And we're supposed to have 2 edges, which we can draw again however we want. So let's just put one here and let's put one here and call this E1 and this E2. So that's the first graph. Now let's look at the second one. V is ABC, and E, the edges are AB, AC, and BC. And so the advantage to naming your edges this way is that you're telling whoever's reading this where the edges are supposed to be, right? Like if your vertices are A and B, edge AB should be between those 2 vertices. At least presumably, right? If edge AB is not between vertex A and vertex B, then, you know, somebody's probably going to be mad at you, and for a good reason. All right, so we have A, B, C, and our edges are going to be AB. There they are. Call that AB. AC, that's that. And then BC, that's that. Okay, so we are drawing graphs now. Okay, now there's nothing that actually requires you to only have like one edge connecting a vertex to a vertex like this. You can have what we call multiple edges. So multiple edge is just more than one edge connecting the same pair of vertices. And if you do that, then your graph is called a multigraph. These names are going to be a little bit important. There's a little chart later on in the notes, and you will have to pay some attention to it, because when you do the homework is going to say stuff like, so homework will say like simple graph, directed graph, multigraph, and you just have to know what the implications of those are. It's not hard or anything. It's just you have to be aware that these names have meanings. So anyway, in this one in particular here, what we're talking about is multiple edges connecting the same pair of vertices. So that's like what's happening right here, right? So we got 1, 2, 3 edges between vertex G and vertex E. And I don't know if there's any others. Also notice that you have a vertex D up here and a vertex F, and there's no edges connecting those to anything else. That's fine. Nobody ever said that you had to have edges on every vertex, right? So just because in the examples that we already drew here, we do, right? There's no what we would call isolated vertices. You can have isolated vertices, perfectly allowed. So yeah, so let's see, let's give this a name, multiple edges, right there, and let's keep going. So now we're talking about what we already talked about, which is loops. And loops are obvious what they are. That's when you have an edge connecting a vertex to itself. So here's a loop, 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 here's a loop. Pretty self-explanatory there, what loops are. All right, now we want to get down here and look at this. We're just, again, kind of taking care of the terminology here. So if you don't allow loops or multiple edges, that is called a simple graph. right? So the one up here, this is not simple because it has loops. This one is simple because it does not have loops and also does not have multiple edges, right? Like there's some multiple edges in there too. So this is simple. No, that's the one that's not simple. Not simple. Simple. All right. Now, sometimes edges have a direction, and so the direction can indicate a variety of things. So on this right here, this is, what is this? So we got cities right here, and I believe that the arrows are indicating like where there are like airline flights where they go. So like if you have flights that go from San Francisco to Los Angeles, then you might put an edge pointing that way. But if no flights go from Los Angeles to San Francisco, then you wouldn't want it to go that way, right? So what they've done is they've only put an arrow down in one direction there. Now, if you need it to go in both directions, then what they'll do, if it's a directed graph, then they will, you draw it one way and then you draw it the other way. So the direction can mean anything at all. The person who's drawing the graph will tell you what the directions mean, basically. So we'll have some examples in a little bit. Okay, so now let's kind of summarize some of the stuff here. We didn't talk in detail about some of these, but you can see them here. So the big ones, of course, are simple graph, which is going to be undirected edges, no multiple edges, no loops. So that's like the most simple thing you can have. Then you're also going to have a lot of multigraphs. Multigraphs, they're still undirected, but multiple edges are allowed, but loops are not allowed. That's weird. Surprised. Where are loops allowed? Oh, they're calling those pseudographs. That this is kind of, sorry, like not talking here, but this is kind of not making me happy here. I'll say you why in a second. So the reason I was staring at this blankly for a second here is because, I mean, this is your book's definitions here, but they've got multigraph, and they say multigraph is undirected, multiple edges, yes, loops, no. So they say no loops in a multigraph. But then down here, they have directed multigraph. Now, it seems that a directed multigraph would just be a multigraph with directed edges, which means that you think that the only difference would be that multigraph is undirected and directed multigraph is directed. So you think that this would be the only difference between undirected and this one, directed. But then if you look over here, they're allowing loops in the directed multigraph, but they're not allowing loops in the regular multigraph. And so that just seems weird to me. And whatever, they did it. So I don't think that will ever be an issue, but maybe it will. Multigraph, no loops, according to this. All right. And then they've added some that you haven't seen before, like pseudograph. So they saved pseudograph to be the graph where multiple edges and loops are allowed. And so that must be why it's not allowed in a multigraph. But whatever. Point of this table is that if you are in the homework and they talk about a simple graph or like a simple directed graph, and then you go, oh, it's a simple directed graph, are loops allowed? And then you can look at the chart and see, okay, no, there are no loops in a simple directed graph. And, and then do the problem. So that's what the table's for, just to keep track of all the different types. Here's something that you must know and understand because we're going to be using this formula a lot. And that is the concept of the degree of a vertex. So degree of a vertex of an undirected graph. And it's just number of edges incident with it. And loops count twice. So that sounds weird, but will we see one? We won't see one right here. I'll have to draw one if I want to. So in the next section, we're going to talk about a bunch of different special graphs, just graphs that have names. And so this one is called Q3, which is a three-dimensional cube. There's also, Q2, a two-dimensional cube, which, forgive the naming, but a two-dimensional cube is just a square, actually. And then Q4 is going to be the last one that you can draw. I don't even know why I'm wasting the time to draw it now, except that I already started. So that's Q3 that I just drew. And let's see here. How do I do this? Okay, they're moving it. How do I copy it? Duplicate. Right? So you draw two copies of Q3, and then you have to connect all the corresponding edges. So that's like bottom left to bottom left, bottom right to bottom right. Not going to be able to understand this very well, but they're terrible looking. But today is not the day that we learn about that. But the point was that Q3 is a special graph, and this is in particular what it looks like. Now, let's just go through and summarize the basic information about this graph here. So how many vertices does this graph have? Right? And there's no trick there. We're just going to be counting these up. So you just go 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices. All right. And then you say, well, how many edges does it have? Well, start over. We got 1, 2, 3, 4 on the top there. 5, 6, 7, 8 on the bottom. And then the vertical edges, we got 9, 10, 11, 12. 12 edges. So you just count them. It's really easy to count and be off by one or something, unfortunately, if the graphs are complicated. All right, now find the degree of each vertex. So now we're actually going to use this definition up here. So the degree of a vertex is the number of edges incident with it. It is the vertex. And loops count twice. So this is easier than it sounds. Okay, so the degree of each vertex, they're all actually all the same, so we can do it that way. But the way you do it is you've got a vertex, right? And you just count how many edges are coming out of that vertex. So 1, 2, 3, right? So that would mean that that vertex has degree 3. And you do that for every one. So like one down here, how many edges does it have? 1, 2, 3. So it also has 3. What about this one? 1, 2, 3. This one, 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. All right, so that's what you're doing when you're counting up the degree of a vertex. And it says the degree of each one. We're not going to write them all separately. We could, but since they're all the same, we can just say they all have degree 3. Okay, so that is the degree of each vertex there. So yeah, now something that you're going to be trying to do a few times in the homework is can you draw a specific graph that has these requirements? So it says draw a graph with 5 vertices. That's actually 6. There are 6 letters there. In which 5 vertices have degree 3 and 1 vertex has degree 5. Okay, so at least that makes sense. So, all right. So let's try to do it. And there's not really a good way to, you know, you don't do anything in advance to prepare. You just start drawing it and hope for the best, right? So we've got, these are our 6 vertices, A, B, C, D, E, F. So you just draw those. You don't know what the graph is going to have to look like. So if you don't know what it's going to look like, a good strategy is just to put your vertices in sort of a kind of a circle there. A, B, C, D, E, F. Because a lot of the other shapes, right? Like if you put them like this, like if it turns out that you have a lot of edges going from way over here to way over here, then you end up with edges like it's hard to draw because stuff is in the way. So if you put them in a circle, then the edges that you draw are less in the way of the other edges that you draw. So that's just strategy there. And that's really kind of the only strategy that we have so far. So let's get going then. So what are we doing here? We are 5 vertices are supposed to have degree 3, but 1 vertex is supposed to have degree 5. Okay, so if 1 vertex is supposed to have degree 5, maybe we can draw that first. So let's go ahead and try to do that. So let's just pick a vertex and make it have degree 5. Let's make F have degree 5. So let's just, degree 5. Let's just make F have degree 5. So that means it has 5 edges. So let's draw 5 edges and let's actually go to all the other vertices. Why? I mean, why not? So like 1 edge, 2 edges, 3 edges, 4 edges, 5 edges. Okay, F is done now, right? So F has degree 5. Now the others are all supposed to have degree 3. So that means every other edge needs 2, like every other vertex needs 2 more edges. And you know, how are we going to do that? I don't know. Let's just try it and we'll have to erase maybe. So like A right now has 1 edge, right? Just this edge. So it needs 2 more. Let's just make 1 go to B. And let's make 1 go to C. Right? So now A is done. So that has degree 3. Right? 1, 2, 3. So now let's move on to B. Let's make B have 3 edges, right? Because it's also supposed to have degree 3. So B has 1, 2 right now. So it needs a third. Where are we going to draw the third? I don't know. Let's just draw it to C. So now B's done. B has 3, degree 3. Let's move to C. C has 1, 2, 3 already. So C is done. All right. We can't do anything to C because it's already got 3 edges. So let's move on and go to the last one here. We've got D. D has 1 edge. So it needs 2 more. So I can draw 1 more there. But actually now D needs another edge. So what are we going to do about it? Well, I can't do this, right? Because if I do that, now D has 3, but then I've messed up C and given it 4. So that edge won't work. So we have to erase that, right? So what are we going to do? In fact, all of the other edges are already essentially done. So the only thing we could really do if we don't want to erase a lot is put an edge here. Make another, like a second edge there. Now, it doesn't actually say anything. I didn't say a simple graph, right? I didn't say a simple graph. I didn't say anything like that. I didn't say multiple edges are disallowed. I didn't say loops are disallowed, nothing like that. So we'll just do a multiple edge here and that'll be done. So then this has 3, and this has 3, and this has 3, I hope. So that's my graph. Now, is this the only graph that meets these requirements? Probably not. If we were smarter about it, could we have drawn a graph that a simple graph that met the requirements? I don't know. I mean, there are theorems that tell you that, but we didn't use the theorems because we don't know the theorems. So we drew this graph. All right. Anyway, we're done. We did it. So let us move on here. So you can use graphs to represent, certain types of information. And one type of information is in social networks. So you can keep a graph of everybody's name. Everybody is a vertex. And then you can just draw a line like this if they know each other. So on an acquaintanceship graph, it'll say that, but it's just going to be acquaintanceship. It's just whether two people know each other. That's basically all it is. So there's an edge if they know each other. Okay. And yeah, so here's one. So they're very straightforward. It's symmetric. There's no direction here on an acquaintanceship graph, right? Because if Eduardo and Paula know each other, then if Eduardo knows Paula, then Paula knows Eduardo. So you just use one edge. You don't have to have like an arrow pointing at Eduardo or an arrow pointing at Paula. Just if they know each other, you put an edge. All right. Then you can have an influence graph. So an influence graph is kind of the same thing. It's a little more complicated. In this case, we can scroll down and look at it. Certain people can influence the thinking of others. So in this case, directed edge from vertex A to B, where the person represented by A can influence the person represented by B. So you have to get the direction going the right way. So A influences B, right? So if it goes from A to B, right? From A to B, then A influences B. So you should be able to look at this graph and like you see this right here, and this tells you that Brian can influence Linda. And then down here, you've got Brian pointing at Yvonne and Yvonne pointing at Brian. So Brian influences Yvonne and Yvonne influences Brian. So you can have multiple edges where they both can influence each other. Okay. And that's an influence graph. And so graphs like these are actually used, like far more complicated graphs than these are actually used, right? This is what, things like Facebook and Twitter and all that, use to, well, mostly Facebook and stuff like that. What they'll use to identify people that like if Todd doesn't have Facebook because Todd is smart, right? Facebook actually still knows that Todd exists because they can tell that there should be a vertex here that all these other people know, and that he's just not in the system. And that's how they make like shadow profiles for people, by recognizing that there has to be a person here and they know all about the person, except that person doesn't have an account with them. But the graphs are a lot more complicated than just an acquaintanceship graph, right? Because like Facebook keeps track of everything that people like and everything that they don't like, and it knows, it knows a lot more than just which people can influence you and which people you can influence. It knows how much you can influence them, and it probably knows what topics you can influence them on, and on all kinds of things. So, these are just kind of like the really basic ideas that get used in these, giant networks like Facebook for, stealing your personal information, basically. So, but anyway, they have these. So let's try to draw a couple of these graphs. So we've got an acquaintanceship graph here. Represents Tom and Patricia. Tom and Patricia and Hope and Sandy and Amy. Okay, lots of people here. So let's just start drawing them. So again, if you don't know how to draw it, then start drawing your vertices in a circle. So every person is a vertex. So you have Tom, just going down the list. Patricia. I was right, Pat. No, I won't. Tom again. Hope. There's a new person. Tom again. Sandy. Amy. Jeff. Mary. Is that new? Yeah, that's the only new one. Okay. All right. So those are our people, and then we need to start just adding edges if they know each other. So just go down the list here. So we have, let's erase these. So let's do this. So Tom and Patricia, boom. Tom and Hope. Tom and Sandy. Tom and Amy. Tom and Marika. Jeff and Patricia. Jeff and Patricia. Jeff and Mary. Patricia, Hope. Amy, Hope. Amy, Marika. Okay, so there you go. There's your graph. So which graph property tells you which person knows the most people? So the only properties we know about now are number of vertices. That doesn't tell you who knows people. Number of edges. That's the total number of edges for the graph. That doesn't tell you anything about who knows the most people. And degree. And degree is how many edges for each vertex. And so that does tell you who knows the most people, right? If you just add up the edges here, right? Mary has degree 1, Jeff has degree 2, degree 2, degree 3, degree 1, degree 3, 1, 2, 3, 3, and 1, 2, 3, 4, 5, right? So which property tells you which person knows the most people? It is the degree of each vertex. Just the degree of the vertex, actually. Okay, degree. That's the answer. Okay, use the influence graph on the previous page to answer the questions. Who can influence Fred? Okay, so we're looking at the one that's drawn up here. Who can influence Fred? So here's Fred. Who influences Fred? So remember, if you can influence somebody, then the arrow points from you to them. So which arrows point to Fred? So there's one, right? This one. So Deborah influences Fred, and this one. So Yvonne influences Fred, right? They're pointing at Fred. And that's the way it works, right? Deborah influences Fred. Yvonne influences Fred. All right, so we can come down here. Who can influence Fred? Deborah and Yvonne can influence Fred, whatever his name is. That guy, you know. The next question is, who can Fred influence? Fred can influence, I don't know, scroll back up. Looks like this is the only one, right? Fred can influence Brian. And that's all you do with those. Not a lot. We've got one more type of graph here, niche overlap graphs. And so these are going to be a graph that's going to keep track of things like competition between species in an ecosystem. So undirected edge connects two vertices if two species compete. So like they compete for some kind of food or something. So so I just copy pasted this from the homework, I believe. That's actually why there's like weird spacing there. And so we're going to construct this. So how do you do a niche overlap graph? So it says it. So we have the interaction of different species of animals. So in this case, we're talking about birds, and we just, every species is a vertex, and then there's edges if they compete. So we just go down the list here. So this is just like drawing the acquaintanceship graph, really. So what do we have? 6 species of birds, hermit thrush. I'm just going to write thrush. Robin, blue jay, mockingbird, I wrote brid, blue jay, we already have blue jay, nuthatch, and hairy woodpecker. Nuthatch and hairy woodpecker. So interesting names they have chosen. Again, straight out of the book. I didn't invent them. All right. So there are our vertices, and then we just draw edges wherever we are told that they will compete. So you just start back at the beginning here. So hermit thrush competes with the robin and the blue jay. So thrush, robin, and the blue jay. All right. Then next we have robin competes with mockingbird. Robin, mockingbird. Mockingbird and blue jay. Nuthatch, woodpecker. Is that all of them? Hold on, let's look. Hermit thrush, robin, and blue jay. Okay, we did that. Robin with mockingbird, we did that. Mockingbird, blue jay, we did that. Nuthatch, hairy woodpecker. Yes, those go together. All right, so there's our graph. And so like a graph like this tells you a lot, right? Like there's a lot of competition between these species. And over here, these species are forming their own group. And so you can see that these species are separate from these species. So there must be a lot of foods in common over here that they eat, but then these don't eat the same foods as this group at all. So, you know, graphs like that help you see stuff like that at a glance. Like it lets you group these. All right. And yeah, so there's more stuff down here involving like adjacency matrix. and stuff like that. I don't think we're going to draw this here. We're gonna wait until the next lecture, and then we'll talk about adjacency matrices. Okay, so for now, not now. Okay, that's in another section. It's not in section 10.1. I don't know why I put it in this set of notes. Okay, so that's it for today. What are you supposed to know? Well, what is a graph? What are things like loops, multiple edges? Degree of a vertex should make sense to you. And also these things, niche overlap, acquaintanceship, and influence graphs should all make sense to you. The homework just asks you some simple questions like these, like, it'll show you an influence graph and ask you a couple of questions. It'll show you, or it'll ask you to draw an acquaintanceship graph of your own. It'll ask you what are the degree of certain vertices in a graph, and so on. So very straightforward, much easier than the proofs that you've been doing up till now. And yeah, I mean, hopefully it's a nice change of pace for you guys. I'll talk to you guys later, where we're going to have, at least 3 more lectures on this topic.